procedures. In lesson 6.1, we talked about sequences and term numbers, and we decided that there is a way, there are formula that can help us to get from a term number to the value of that specific term. Something like that would look like this, okay? It's just a function, it's an explicit function, which means it gets us from the term number n directly to the value of that term using this relationship. All right, this is just a random example. This is not the same sequence down here, but today what we're going to be talking about is a recursive procedure, which essentially doesn't get us from any term number to its term, but it gets us from a given term to the next term, okay? So this is just an example. The first term in this sequence is 3, and to get any term, t of n, t sub n, you simply take the previous term, t sub n minus 1, and add 6. So for this simple example, the second term of this sequence is simply the term before the second term, which is the first term, which is 3. So 3 plus 6 is 9, okay? The third term, we would simply take the previous term, which is 9, and add 6, 15. Okay, this is a simple example, but that's what it means to have a recursive procedure, that you can start at a given term and you can get the next term, okay? Let's start by doing the investigation that you see on that page, on your notebook, page 6, and I will get you started on that and then allow you to finish up on your own. So what we're going to do in this investigation is start with what's given, and we're going to model a sequence using the side lengths of given squares, okay? And how this pattern works is that we start with this first diagram, which is diagram number 1, has a side length of 1, okay? What we're going to do is we're going to just start off to the left side, and we're going to take the side length of diagram 1, and we're going to add a square of that side length, okay? Now, that becomes diagram 2. So what side length does diagram 2 have? Well, diagram 2 has a side length of 1, okay? Because it's still just a 1 by 1 unit square there. But now we're going to go around and around and around, and we're going to go ahead and draw another square using the side lengths of the diagram that we have. Okay, this is now diagram 3, and it has a side length of 2 units. Working around our circle, okay, and maybe I can label my diagram so that we're all on the same track here. I'm color coding. You don't need to color code. I just hope that's easier for you to see. Now my next diagram has a square with side length of 3 units. Okay? So there we have it. There's diagram 4. Diagram 4 has a side length of 3 units. And now as I'm working around and around and around, I'm going to get more colors out because it's fun. And I'm going to draw the next square so you can see we're kind of curling around. The next one is going to have a side length. Well, if side length of diagram 4 was 3 units, 3, 4, 5. So I now have a square with side length 5 units. You're going to count yours out to be exact, but my 5th diagram has units 5 side length 5, and my next one is going to have 5, 6, 7, 8. So a square with side lengths of 8 units, but that's diagram number 6. And you have space on your page to do one more diagram. So we'll head down to the bottom here. We've got side length of 8 plus 2, it's 10, plus 3, that's going to be 13 in diagram 7. I think this one actually extends one row past where you have space for, but that's okay, just add another row there. And this is diagram 7 with side length 13. Now you can see this is a growing pattern. It would be difficult to get the side length of your 7th diagram based on any kind of direct explicit function, but you can get it based on the previous diagrams. Okay, if you came up with a recursive formula, you could work toward that, and that's what we're going to do now. Okay, so we're going to take a look at the sequence that we've created, and down at the bottom of your grid there, you could even figure out what the 8th diagram is going to look like. So the 8th diagram has 13 plus 3 plus 5. Okay, oh, that's actually, look, 13 plus 8. Something to look for in that pattern. Let's see if we can find a pattern. The bottom box says determine a relationship between consecutive terms. So going from this term to this term, and this term to this term, this term to this term. Is there a way to get from a given term to the next term? All right, I'm hoping you've come up with something. And basically what we're looking at is how to get to the nth term using previously determined terms, okay? So we're going to talk about it in terms of the n minus 1 term and the n minus 2 term, okay? So actually all you need to do to get the term 13 is add 8 plus 5. Well, let's see if that works for other ones. To get 2, you just add 1 plus 1. To get 3, you add 1 plus 2. To get 5, you add 2 plus 3. And all the way down the list. 21, you just add 8 and 13. You could probably figure out what the 9th term is going to be. Just add 21 and 13. Okay, the 9th diagram, if we kept going around and around, would have a side length of 34 units. So what do we do to get the nth term? Well, we took the value of the term preceding it plus the value of the term preceding that term. So this represents the 2 terms that come before the nth term. Now, it's a recursive formula or a recursive procedure because you actually need both of these 2 terms in order to figure out that term. You can always figure out the next term and the next term and the next term, okay? So that's the basics of what we're working on today. And just to make sure that you have all the notes that you're supposed to have, the top right box of your chart at the bottom says write the side length of the squares as a sequence. So that would look like all of these numbers written in a row using commas. So you'd have term value 1, term value 2, term value 3, okay? And you just write all the terms that you have in order, and you might go comma, dot, dot, dot to show that it continues. Well, it turns out that the sequence that we worked with in the investigation is actually a very famous sequence. It's called the Fibonacci sequence. So wherever you can find a few notes, a space for some notes. Sorry, I know the book is a little bit tight, but maybe at the very bottom of the first page there, or else, I don't know. Find somewhere to put these notes. There's not a lot of them. But the Fibonacci sequence, something you need to know about. And this is one of the things in math that is honestly so striking, and that is just a testament to the greatness of our God. He is a God of order. He is a God of patterns and of systems and of rational thought. And just the way that I'm going to get you to watch a video on the Fibonacci sequence. It's not done by a Christian, but it certainly reveals the many things of creation that God used this sequence. It's not Fibonacci sequence, it's God's sequence first, that he used in creation and in the many different things that have been created, and it will hopefully just blow your mind. Anyway, the Fibonacci sequence, 2 notes. The sequence of numbers, 1, 1, 2, 3, 5, 8, 13, ... And how did we get there? Well, each term is generated. Each term is generated from the preceding, sorry, I'm mixing up. How did we get there? Each number after the first 2 numbers, each number after the first 2 numbers is the sum of the preceding 2 numbers. Each number after the first 2 numbers is the sum of the preceding 2 numbers. We already talked about that. How do you get 13? You add up the 2 preceding numbers, the 2 numbers that come directly before 13. 5 plus 8 is 13, okay? Now, the Fibonacci sequence is simply a very well-known special kind of recursion formula. So your next note is on the term recursion formula. This is a formula, we've already described this, but now you have a note on it, a formula by which each term of a sequence, a formula by which each term of a sequence is generated from the preceding term or terms. A formula by which each term of a sequence is generated from the preceding term or terms. All right, that means you need to know previous terms in order to get the next term and keep the sequence going. Example 1. So we're asked to write the terms of a sequence given the recursion formula. And there's not much to this. We're going to write the first 4 terms of each sequence. And we're going to look at A first. The recursion formula has 2 parts. It has the given first term and how to get the subsequent term, okay, the next term. So here we go. Term 1 is given, not too hard. So let's develop the next 3 terms. Term 2 is going to be term 1 minus 2. Okay, this is just the previous term, which in this case is term 1. Well, term 1 is 3. That's given. Take away 2 equals 1. Okay, so the second term is 1. I'm going to work down. In your notebook, it's lined up so that you can work across, and you'll clearly see, term 2, term 3, term 4. But in order to not smudge my work, I'm going to do the second example down on this side. So now I'm looking at term 3. Term 3 is simply the value of term 2 minus 2. I already found out that the value of term 2 is 1 minus 2 is negative 1. Next, term 4. Simply term 3 minus 2. Term 3 is negative 1 minus 2 is negative 3. There you have the next 3 terms. So the first 4 terms of the sequence are, the first term was given, that's 3. Then we had 1, -1, and -3. Let's go across the way. In this term, the first term is given as -1/2. And in order to get the second term, all we're going to do is take the first term, which is the preceding term here, and add 3/2. All right, well, first term is -1/2. We're going to add 3/2. That's going to give us 2/2 or 1. Okay? The third term is going to be equal to the value of the second term plus 3/2 or 1.5. So yeah, you can do this two ways. You can right away write the fraction. If you need help adding fractions, you need a common denominator. I'm not going to worry too much about that. We're going to work through this a little bit more quickly. So we have 1 plus 1.5. That's going to be 2.5 or 5/2. Okay? To get the fourth term, we take the value of the third term, add 3/2. See if you can beat me to it. 5/2 plus 3/2 is 8/2, which is 4. All right. Therefore, the first four terms are -1/2, 1, 5/2, 4. Okay, so developing the terms of a sequence when you're given the recursion formula, not very difficult. Just be careful. Take that first term and do exactly what it says in the second part of the recursion formula. In example 2, we're asked to write a recursion formula given a sequence. All right, so A, we have the sequence -3, 6, -12, 24. Not a very complicated one, but what we're going to do is we're going to look for a pattern in these terms. So how am I getting, right, a recursion form is how are you going to get from one term to the next term. So if I'm looking at this -3, how did I get from -3 to 6? And then to -12, and then to +24? I can see that in each case we're going to be multiplying by -2. Okay, so that's the pattern that we've established. Now to get our recursion formula, we know that we need to start with the given term, which is the first term given for us right here, -3. And I'm going to pretend that this is harder and I don't already know the answer. But basically we're going to look at that second term and say, how did we get that? Well, we took the value of the first term and we multiplied by -2. Well, what about that third term? How do we get that? Well, we took the value of the second term, we multiplied by -2. And the same is true for getting the fourth term. We take the previous term, term 3, multiply by -2. Now we clearly have our pattern. For any term, I just need the previous term, multiply it by -2. So the recursion formula is, and I'm just going to directly take what we've established, except I'm going to use n and n-1 for our term numbers. So we've got any term, well, sorry, we need to start with our first term, right? Recursion formula starts with the given term. First term is -3. The second part of it is any subsequent term can be found by taking the preceding term and, in this case, multiplying by -2. Now you look at that and that looks kind of confusing. It's a pretty ugly way to write things in the world of algebra. So I'm actually going to rewrite that. First term is -3, and every subsequent term is simply -2 times its preceding term. And there is our recursion formula for example 2a. In example 2b, you are given just a graph of points that are plotted. I'm just going to jot down the points that you have because I don't have a picture of a graph here. So you have the point, you have the point 1, 2, not 0, 1. You have the point 1, 2. You have the point 2, 6. A little bit tricky because that y-axis is going up by a scale of 2. The x-axis has a scale of 1. So just be careful with things like that. The next point is 310. 310. And the last point there is 414. So again, I have the term number, right? Because our domain is the term number. Term 1, term 2, term 3, term 4. And I have the value of each term. So if I'm going to make a little list here, the value of the function at n equals 1 is 2. The value of the second term is 6. The value of the third term is 10. The value of the fourth term is 14. And now I'm just going to be looking for a pattern. So how am I going to get from this first term to the second term, to the next term, to the next term? In this case, it's pretty easy to see. All we're doing is taking the previous term and adding 4. And if I can develop a consistent pattern that way, then I can create a recursion formula. The recursion formula is starting with the first term. The first term is 2. Then, for any term, you simply need the previous term and add 4. Okay? Example C is a little bit more challenging. We are going to do it the exact same way that we've done it so far. And then we're going to talk about what the pattern, what the recursion formula should really look like for the pattern. So starting again, the first term is given, it's 3. Now how did I get from term 1 to term 2? Well, term 2 is simply the value of term 1 plus 2. Yeah, 3 plus 2 is 5. Now it's not going to be a constant pattern, but it is going to be a consistent pattern. So how do we get the third term? Well, I simply take the second term, and this time I actually have to add 3. To get the fourth term, I take the third term, and this time I have to add 4. So you see I'm taking the previous term, but now the number that I'm adding is not constant. It's changing. It's going up by 1 each time, but can you spot another connection? There is a connection between the number that we add and the term number that we're looking for. Again, there's a connection between the number that we add and the term number that we are looking for. So let's just say if we had to do this a fifth term as a sample, well, we'd be taking the previous term, t of n minus 1, and we'd be adding 5, which is the value of n. Okay, so if we look at this one, we have a recursion formula. Recursion formula. I wouldn't expect you necessarily to write those words every single time. You could just write the recursion formula. First term is given. That's 3. And we can get any term as long as we take the term value before that term and add n. And now this thing that we're adding, this value that we're adding at the end, will increase with the term number, just as it does in our laying out of each term value. Okay, there we go. There's C, and another trick that you can put in your pocket for when you need it. Example 4, we have medication in the human body. A runner has been injured, so a runner has been prescribed 500 milligrams of an anti-inflammatory medicine every 4 hours for 3 days. So she's going to take 500 milligrams every 4 hours for 3 days. The half-life of this medicine is approximately 4 hours. This means that after 4 hours, about half of the medicine is still in the body. Okay, so half of the medicine is still in the body, and then she's going to take another pill every 4 hours. We need to make a table of values showing the amount of medicine remaining in the body after each 4-hour period interval. All right, so you have a table listed for you there. I'm just gonna, now I have one too. And we're just gonna do this paper and pencil style. You could do something like this in a spreadsheet, but basically we're going to do fill in the chart based on what we know. So make a table of values showing the amount of medicine remaining in the body after each 4-hour period of time. It's after the 4 hours. So after no 4-hour intervals have passed, she's taken the medicine, so she's got 500 milligrams in her bloodstream. Okay. Then after one 4-hour interval, two things are going to happen. That's going to be the half-life of the 500 milligrams that she has already ingested, and she's going to take another pill. All right, so we've got half of 500, which is 250, plus 500, which is a total of 750 milligrams. All right, now if we go, and you can see how this is going to be a recursion formula, because now we have this amount, 750 milligrams, and after the next 4-hour interval, that amount is going to be cut in half. Okay, now we don't care how much of that 750 is from the first batch and from the second batch. It's half-life, so it's going to decay at a constant rate, which means all of that 750 is going to be cut in half, regardless of what part it was. Okay, what else is she going to do? She's going to take another 500 milligrams. So we have half of 750 plus 500, which is 875. You can see how the amount is growing, okay? Well, after another 4-hour interval, we're going to have half of 875. She's going to take another pill, 500 milligrams, and she's going to be at 937.5. Go ahead and continue that chart down until the end and regroup and see if you end up with the same final value that I have, 999 milligrams, 0.9. All right, we're rounding to the nearest tenth of a milligram, by the way, on your way down. So go ahead and pause, get that done, come back. That's section A. To complete B, we really just need to take those values that we got in the amount column and write it as a sequence, okay? So here's how we would write a really long sequence when we don't want to write the whole thing. We write the first few terms, 500, 750, 875, 937.5. Then we give a little ... to say, okay, there's a bunch more terms in there. And we're going to keep that sequence going until we get to 999.9, and that will be the end of the sequence. All right. Now a recursion formula. We can kind of think of this two ways, or confirm our thinking two ways. We could look at this and try to develop one, or we can say, oh, we actually already really did develop one. We're just taking half of the previous amount and adding 500 each time, or starting with 500 and adding half the previous amount. So here's what we've got. We've got our first term, which is, be careful here, your first term does not align, does not coordinate with the after the first interval. It coordinates with after 0 intervals. Your first term is 500. Okay, so that's where you're starting. And any subsequent term, you're simply taking another 500 and adding it to what's left in your bloodstream, which is half of whatever the previous term was. All right? C asks us to graph the sequence. You have the graph there. I'm going to leave it to you to give yourself appropriate titles and axes and scale. It might be something like this, 1,500, 0, and then make sure all of your hours fit and you're going to put your points on as you go through, and basically you're going to find out that it looks something like that, okay? Again, you cannot draw a continuous line through it. It is a discrete function, all right? There is no in between these hour intervals. It happens at specific intervals. And then in D, now that we have a good idea of what's going on here, D, describe what happens to the medicine in the runner's body over time. Well, from the graph, we can see that the amount of medicine, if she keeps up this system every 4 hours for 3 days, then what's going to happen? Well, the amount of anti-inflammatory medicine in her body is going to increase until it appears to reach a fairly constant level of about 1,000 milligrams, okay? So in D, just to complete this out, the amount of medicine increases until it reaches a constant level of approximately 1,000 milligrams. What's interesting about this, here's a real-world application. What often happens when you're taking this kind of medicine or when you have to get antibiotics from the doctor's office, rather than being prescribed just one every 4 hours for 3 days, like we were in this case, they'll say, okay, the first time you do it, take 2 right off the bat. So you actually start up here, and then you find out that it plateaus, so that you don't have to deal with this first stretch where it's not quite at the amount of medicine that you actually want in the bloodstream. So you normally do double dose, you can do double dose on your first take, and then do 1 every 4 hours. All right, your practice problems for lesson 6.2 are from page 370. Page 370, numbers 1 through 14.